Alright, so in the last video we saw the notion of sets and the two ways of specifying sets, namely roster method and set builder method. So today let us see some examples illustrating these ideas. In this first example, we are given this equation, this quadratic equation, and we have been asked to write the solution set of this equation in roster form. The solution set of an equation is the set of all of its solutions. That means we need to first of all solve this equation. It's a familiar quadratic equation in one variable, so it can be solved pretty easily. So let's see the solution. We have x square plus x minus 2 equal to 0. Okay, now you of course already know that when you are having such an equation, there are several ways of finding the solution. So we choose to factorize the left hand side polynomial. It's a quadratic polynomial, and let's see if it can be factorized easily. Okay. But if you want, you can of course also use the quadratic equation formula directly. If you cannot figure out any easily doable factorization, okay, then it's better to use the quadratic formula. Here, however, I can see that there is a very easy factorization. The x can be written as 2x minus x. Now, if I take x common out from these first two terms, then I get x times x plus 2. Similarly, I can take minus 1 common out from the last two terms and get x plus 2 again. So here I just wanted to bring one common term. And then what I do, from these two terms, I take x plus 2 common out. And doing that, I get this. So, the solutions of the above quadratic equation are 1 and minus 2. Hence, the required solution set is minus 2, 1. If you want, you can also write here the solution, the required solution set in roster form is this. I have decided to write the elements in this way, where I choose the smaller one first, minus 2, and then the bigger one, 1. But of course, order does not matter. So you can also write 1, minus 2, it's up to you. Note one more thing, that I have not used the usual implies sign, and I have used the double implication. Why though? Actually, strictly speaking, we should really use the double implication. Because if you only use the single implication, it means that if x is a solution of this equation, then x must be those two values. But then you are also left with the task of seeing whether those two values actually are solutions. And that's why I use double implication? Because if someone starts from here, then one should be able to go back to this. In other words, if x is either 1 or minus 2, then of course this product is 0, because then either this is 0 or this is 0. But then if I can go back to this, that means yes, those two values actually satisfy the equation. So I prefer to use double implication in any such situation as much as I can. But anyway, that is the solution. So let's now see the next example. Write the set a set is given in set builder notation, and the set is this: x such that x is a positive integer, and something else is also given, and the square of x needs to be less than 40. This set in roster form. So it's given in set builder form, we have to write the same set in roster form. And for that, of course, we need to know precisely the elements of this set, so that we can make a list of them. So here we are dealing with the set of all positive integers. See, every condition is important. X is not just positive, it's a positive integer. It cannot be a fraction, or it cannot be an irrational number, such that its square is less than 40. Since positive integers start with 1, so we one after another we see the squares of the first few positive integers. 1 square is of course less than 40. 2 square is 4, that is also less than 40. 3 square is 9, still less than 40. 4 square is 16, still less than 40. 5 square is 25, that is also less than 40. 6 square is 36, still less than 40, but I think we have reached the limit, because the next square is not less than 40, it's greater than 40. So the x's that we can have in this set are 1, 2, 3, 4, 5 and 6. That's it. These are the elements. Now, since it's pretty easy to see what the elements here are, so instead of doing anything, we can straight away write the set in roster form, like this. The given, it's unlike the previous example. In the previous example, we at least had to do something to find the solutions. Here, however, we can do, of course, we had to go through this thing, but it can be checked mentally also. So the given set in roster form is this. Now, you may have a tendency to write ... here, but please don't do that, because we have only a few elements in this set. If the set can be written manageably, and even if it has say 20 elements, it can be written, it's feasible to write the set, that is writing all the elements, then please do so. We use dot 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 only when it becomes unmanageable. Next, example 3. In the third example, we are given write the set. Now an infinite set is given. Okay, there is a name also. It's been called A. So it goes on like this. In set builder form, so many elements have been shown. You see, in case of writing an infinite set in roster form, we generally do not write more than 3 elements. But because we need to be able to figure out the pattern in which the elements are going, that's why 5 elements have been shown. And you can clearly see the pattern. These are nothing but squares of the natural numbers, squares of the positive integers. So you can understand that after this 36 will appear, and then 49 and so on. That's why the given set A, in this time we have to write it in set builder form, it's given in roster form. In set builder form, is this x such that x is equal to n square, where n is a natural number. You can either write like this, or as we discussed in the previous video, there are many other ways of writing this. In fact, this looks like we are writing too much. The solution ends here itself, but the same set can also be written like this. N square, where n is a natural number, means that fact can also be expressed by simply writing this n belongs to n, the set of natural numbers. Or you can also write like this in an extremely brief manner. You can write the same set like this. However, it's advisable to not write like this right now itself at this elementary stage. You better write this, or you can also write like this. Okay, do not make it too brief. You see, technically there is no distinction between this and this, but from an examination point of view, whoever is going to check your answer script should not feel that you just don't know the thing. Okay, so it's better from an examination point of view to be a little descriptive, not absolutely brief like this. But anyway, let's just see the next example. Examinations are just destroyers of subjects. For the sake of examinations, we have to do many things which actually do not make any sense at all. Write the set. Next, we are given this set. Three over 4, 4 over 5, 5 over 6, and finally 6 over 7. This set in set builder form. Here also, unlike that one, this is a finite set, only finitely many elements, in fact 6 elements. But just like that previous one, here also the pattern is clear. We know in what pattern these numbers are appearing. See, because order of the elements appearing in a set in roster form does not matter, had they wished, they would have written this in a jumbled manner also. Say, writing 6 over 7 as the first element in this way of writing. After that, say they write 2 over 3, then follow that up with 1 over 2. That could also have been done. That will actually be very confusing until one rearranges them in this fashion and then sees that, okay, it has a pattern. But of course, it's given in a very nice manner. So we can immediately see the pattern. The pattern is just this. These are all rational numbers, where the numerators increase by 1 and the denominators are 1 more than the numerator. Note that the numerators start at 1 and increase by 1 and finally reaches 6. So accordingly, we will write this in set builder form like this. The given set in set builder form is this. It's the set of all elements X such that X is of this form, where n is a natural number and n is less than or equal to 6. Will that really give me this set? Let us see. Note that in the text, this, instead of this inequality, these two inequalities are written. However, that is not necessary. This part is unnecessary. The moment you say that n is a natural number, that automatically means that n has to be greater than or equal to 1. So if you want, you can write like this, that n is a natural number and this. However, when you write this part is in fact not necessary. But simply writing these two inequalities is not sufficient. Why though? That's because who will know that you mean n to be an integer, a natural number, not a fraction? If you simply write like this, no, many fractional numbers also satisfy this inequality. For example, 7 divided by 2 also satisfies this inequality. Now in place of n here, if you put 7 over 2, you won't get any of these numbers. That's why it's necessary to mention that n is a natural number, and then it's up to you to decide whether you write this part or not. I choose to not write this one here. So for me, this is the set. And this is the solution, but of course again you can make this shorter by writing like this, such that n is a natural number, and instead of writing and you can also write comma. Okay, same set. And finally we have this fifth example. Match each of the sets so two lists of sets are given, same list actually, but in one list the sets are expressed in roster form and in the other they are written in set builder form. So we have to match them. On the left, in roster form, with the same set, on the right, in set builder form. And the lists are like this. Well, in order to make things more clear, let's draw a vertical line in between so that we can clearly distinguish the two lists. So the first set in the first list consists of these letters . The second, of course, I cannot write the entire thing here itself, is the singleton set 0. A set is said to be singleton if it has only one element. Okay. Then the third set consists of these numbers 1, 2, 3, 6, 9, 18, and there is a fourth one also. It has two numbers 3 and -3, and on the right side we have these sets. The first one is the actual way, the way these sets have been written in the text. It has a lot of words, okay, but I am going to use symbols. Ultimately it will have the same meaning, only it will take less space for me to write them because I am using symbols. B, X such that this and x square minus 9 is equal to 0. The third one is the set of all x such that x is an integer and x plus 1 is equal to 1. And the fourth one, so because of using symbols, I have been in fact able to write so far without running out of space, but now I think can I manage in this small space? X such that x is a letter, of course not. In the word, I have to go on that side. Let me just simply continue D from here. In the word, principal, we should not use full stop here. It's pretty clear which one is which. For example, 1 is the same set as the one in D. Okay, so the sets in 1 and D are the same, but let's verify also. If you write the letters in this word principal without thinking about repetition, then in roster form, of course, it looks like this. Now, if you start deleting repeated letters, first you have a P here, so you delete it. Forget about the commas, okay? R is not repeated. I has been repeated, so let's delete this I. N is not repeated. C is not repeated. A and L are not repeated. And then you see whether you are really getting those same letters here. P, R, I, N, C, A, L, N, C, A, L. Okay, so this is how in fact they also got this set. First writing the letters in their natural order in which they appear in the word, and then deleting common letters. Common letters means repeated letters. Okay, next. What about this one? This one will be the same as this one, because if you think of what will happen to x here, this is also after all an equation, an extremely easy one, but nevertheless it's a linear equation. And if you solve it for x, you get 0. So that is why this and this are the same set. Those in 2 and C are the same. Next, what about this? This will be the same as this one. What is that set? That is the set of all natural numbers, that means all positive integers which divide 18. You remember this notation. If A and B are two integers where A is non-zero, then this means that A divides B, or that B is divisible by A. So the set you see here is the set of positive divisors of 18, and these are precisely the positive divisors of 18. 1, 2, 3, 6, 9 and 18. And okay, can we verify that also? You also recall we talked about a little way of simplifying the task of finding the positive divisors of a given integer. What you do, you have the integer, you start with 1. 1 divides everything. So you then divide the integer itself by 1, you get the integer itself. That is also a divisor. 18 is also a divisor of 18, just like 1 is a divisor of 18. Next, we test 2. 2 of course divides 18. Then you divide 18 by 2, you get 9. That is another divisor. 3, 3 also divides 18. And that gives you the other divisor 6. 4 does not divide 18. Okay. 5 also does not divide 18. 6 divides 18, but you have already got 6. So that's it, because you have got 6, 9 and 18 already. And that is why these are the only divisors. And you can see them here. Those in 3 and A are the same. And finally, of course, the sets in 4 and B are the same. Why? This is the set of all integer solutions of the equation x squared minus 9 equal to 0. And you know that these are the integer solutions. That's why. And those in 4 and B are the same. So that is the solution. And here this small section ends. After this we have the exercises at the end of this section. And we will solve the exercises next week in the community section. So please check the community section, the exercise solutions will appear there. So that's just it for tonight, folks. See you in the next week. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.